Hi all, welcome to iitiansgateclasses again. So in the previous lecture, I actually explained like how can we solve recurrence recursive relations, right? For example, if it is given that the recursion relation is Tn equal to Tn minus 1 plus 1. And there could be some base condition, like if n is greater than 0, then this is the condition. If n is equal to 0, then it's 1. Okay. Now I explained like how can we solve these things. Okay. But if you are given with a recursive function, okay, if you know how can we write a recursive function for a given problem, then how can we convert that recursive function into a recursive relation? Okay, so let's take an example for this particular recurrence relation. So if a given function is factorial, we are calculating factorial. Okay, and the function is FACT n. Okay, so in this function, if we pass n, it will return us the factorial of n, right? So we know that factorial of 1 is 1, right? And factorial of n is basically n minus 1, n minus 2, n minus 3 till 2, 1, right? Like this. So this is the factorial of n. So let's again write a recursive function for this. Okay, how can we write a recursive function for this? Then from that recursive function, we will write this recurrence relation. We'll write this recurrence relation. Okay. So what can we do? We can write it like factorial of n is equal to, if n equal 1, then return 1. Else call the same function, right? Call the same function. N multiplied by as return n multiplied by factorial of n minus 1. Okay, so this is the recursive function. What is recursive function? A function that calls itself, but the input size will be reduced in the next calling function. Okay, so this is the next calling function, and we reduce the input size by 1. Okay, so now for this function, we can build a recursive tree to calculate time complexity. Okay, and we can check for the master theorem if we have recurrence relation. Okay, and from recurrence relation, we can also try substitution method, which I explained for several examples in the previous video. So right now, if you see effort here, the computation effort is only 1. Like we are only multiplying. Even if it's go here, it's order of 1. This computation, this n multiplied by fact n minus 1 is also order of 1, right? But it depends like how many times we are going to call this factorial. So let's build a recursive tree for this particular recursive function, right? So let's have a node where the input size is n and the time complexity is order of 1, right? And this function will call on input size of n minus 1 and time complexity is order of 1. Then again, it will be called on n minus 2. It's order of 1 till 1, right? Order of 1. So this is the recursive tree for this recursive function, right? Effort at each level is order of 1, and the number of levels are, in recursive tree, we can calculate time complexity as effort at each level multiply by number of levels. So number of levels are basically n and effort is 1. So time complexity is order of n. This is the time complexity using recursive tree method. Now let's see the substitution method. So this is worst time complexity. Okay, worst case time complexity. The worst case time complexity is denoted using order of n, right? This is the worst case time complexity. Now, if we use the substitution method, it's basically order of n plus 1, right? So let's substitute this with the same thing again. So here we will have something plus 1. This one is the same one. So it will be t n minus 2. If we replace n to n minus 1, it will be t n minus 2 plus 1, right? So it will be t n minus 2 plus 2. Now we will replace n here with n minus 2. So it will be t n minus 3 plus 1, right? Plus 2 equal to t n minus 3 plus 3, right? So if we reiterate this step n minus 1 times, we will have t n minus 1 plus n minus 1, right? Right. So t n minus 1 plus n minus 1. This can be written as t1. And t1 we know for the factorial is 1 plus n minus 1, which is n. So it's order of n. Okay. So this is how we can apply substitution method also. If we know the factorial, we can use the same thing and try to convert this into a recurrence relation. So how this recurrence relation is achieved? At each step of the recursion, the effort is 1. Okay, and we're reducing the size. We are calling the same function. So you can assume that this factorial is basically t. Okay, so at each step of the recursion, we are calling reducing the size by n minus 1, and the effort is 1. Right. So this is the recurrence relation. This is the recurrence relation we can achieve. So let's consider one more recursive function. Here. RF has a recursive function here. I will write recursive function in black and the recurrence relation in red. So if you see that we are given with this some function n, right? And here we are saying that if n is less than equal to 1, return 1. Else do fun n by 2 only. Okay, and we can do like plus 1. So given a recursive relation with recursive function, which is basically calling itself here like this, they can ask you the value that this function returns. This will I cover in programming part. Okay, or they can ask you the recurrence relation. Now recurrence relation for Tn, what will be the recurrence relation? We will say that if n is less than equal to 1, it's 1. Else means n is greater than 1. We are reducing the input size by n by 2, and the total effort is order of 1. So we can write it as 1. Or you can write C also. It's the same thing. C means some constant effort we are doing. 1 is C only. It's C. Okay. So this is how we can write recurrence relation for this one. And I already solved Tn equal to Tn by 2 plus 1. What is it? If you remember it, it's basically log n, right? It's log n. You can check the previous video where I solved it using substitution method, or using master method also you can solve it, right? So what is the master method value here? What does master method say? A T n by b plus some fn is here. Then there are three cases, right? If you remember, there are three cases. So right now, this is the last case, Tn equal to Tn by 2 plus 1. This is the last case, right? What is the value of A? A is equal to 1. What is the value of B? B is equal to 2. And Fn is 1 here, right? Fn is 1 here. So using this recursive method, we build a recurrence relation, and we are solving this recurrence relation to calculate the time complexity. Okay, or you can say the effort taken in asymptotic notations. Okay, so if you check the criteria there, it is given that A can be greater than or equal to 1, B should be greater than 1. Okay, and Fn should be polynomial. So it's polynomial, n to the power 0 is polynomial, n to the power 0 is 1, right? So all the criteria are satisfied. All the criteria are satisfied here. So we can apply master theorem. So it's the case number 3. How it is case number 3? Fn is n1 equal to n to the power 0. And n log base ba, what is it? N log b is 2, a is 1. And you know that log 1 is 0. So it's n to the power 0, which is 1. Now we know that Fn is theta of n log base ba. If this is the case, then our answer is order theta of n log base ba log n. Or if these two are already equal, Fn and n log base ba are equals, we can write it like Fn log n also. Okay, so Fn log n is basically n to the power 0 log n, which is log n. Okay, so why did I solve this recurrence relation again? Because we are going to use the same recurrence relation. We are going to develop the same recurrence relation for binary search. So binary search is a divide and conquer problem. The generic divide and conquer format I will explain in just a minute. Before that, let's look into the binary search. So when can we apply the binary search? If a given array is sorted, condition 1 is if given array is sorted. First condition should be satisfied, sorted. Right, in ascending or descending order, it doesn't matter. You should know whether it's ascending or descending, but it should be sorted. And we want to find a number. Okay, what do we want to find? You are given a number k. You need to find what is the index of this number in given array. Okay, so you are given with a sorted array and you are given with a number. You have to find the number in the array, the index of that number. Okay, so what is the simplest way to find it? First thing is what you can do. Okay, let me give you an example, simple example. Okay, so for example, you are given with a array which is something like this. Array is 10, 23, 25. Okay, then we have 44, 50, some random increasing number. So we know that this array is sorted in ascending order. 50, 78, 91, something like this. Okay, so these are the array numbers. Array indexes generally we denote it starts with 0. Okay, so once we cover the data structure, we will also cover generally why do we say that it starts with 0 and not with 1. Okay, 1, 2, 3, 4, 5, 6. Right? If these are the indexes and you are given that, you need to find whether a element, for example, 44. Okay, so first question is basically if 44 exists in the array. Okay, and if it exists, then what is the index? Array index, right? So if you face these problems, then what is the simple way? What is the simplest way you can find 44? You will check, we will compare 44, k equal to 44. You will compare k with 0th element. Okay, then you compare k with first element, then second element, then third, then fourth. Okay, so you find out that, okay, the third element is equal to k, and I know that I will return that index is 3, right? So if you say that, okay, let's see the k value is 45. K value is 45. Let's try to find out if 45 exists in the array. And we know that array is sorted. So we'll compare it with 0th index, 1, 2, 3. And when we come to the 4, 45 is less than fourth element, right? So we know that, okay, 45 didn't exist. We will return -1. -1 indicates -1 is less than 0, right? It indicates that this element k equal to 44 doesn't exist in the given array, right? So what is the time complexity here? What is the time complexity here? So let's write an algo in terms of recursive relation. Algo in terms of recursive relation for this kind of search, where we start with 0th index and we'll end up to the last index by comparing each element with k, and we know that whether we will know that whether k exists in the given array or not. So what could be the simplest algorithm? This is called linear search. Linear search algo. Okay, you are given with array A. This is the array A, right, which contains all the elements. Okay, and you are given with the index, current underscore index. This is the current index and the size of array. Okay, this size of array depends upon, with size of array, we will also pass the number that we are looking into the array. Okay, which is k. So size of array in some language you don't have to pass because you can calculate the size of array using some functions of the language. For example, a dot size. Okay, in some language we can pass the size of array. So this is an algorithm. So algorithm contains some rough sequence of steps, not exact the programming code. Okay, we say that if a current index is equal k, this is the base case. We found the element, right? We found the element. So we will return this current index. Else else. What we will do, we'll call this function again. Else if you check that current index is greater than or equal to n, we say that the whole array has been scanned and we didn't find the element. We didn't find the element k in the array, and we'll return -1. So we'll optimize this one again, right? And in the else, we'll say that return okay. Here the current index is greater than n, so we scanned the whole array and we are saying that let's return -1. Okay, in the else part we'll say that okay, let's call this linear search again. Linear search again by reducing the input size. Input size is reduced. Right now input size is the iteration from current index till n, right? So we'll increase the current index plus 1, okay, n comma k. Okay, so this is the basic linear search algorithm. So in the linear search algorithm, it doesn't matter whether this array is sorted or not, right? It doesn't matter. How much time complexity will it take? It will take order of n. Okay, so we can build a recursive relation, the recurrence relation for this also. So let's try to build a recurrence relation for this linear search function. What could be the, I can denote recurrence relation as RR. What is the recurrence relation for this one? Right, so Tn, what is the effort taken right now? Let's skip the base condition right now. What is the effort? In each step, we are increasing the value of current index by 1. Okay, in each step. Initially, it will be 0. When this function is called, this will be 0. Current index will be 0. Okay, we will scan from 0 to n. And how are we scanning? How are we scanning from 0 to n? By increasing the value of current index, because we are checking the value of current index with k only. Okay, so what is the effort taken? If you see, the effort is constant, it's C, constant effort, right? So here there is no loop here. And here also, we are not doing anything else apart from calling this recurrence relation again. So what is the effort for this recurrence relation? It is T n minus 1. Okay, because we have reduced the size of search space. Previously, the search space size is n. Now it's 1 to n, so it will be n minus 1. In the next iteration, in the next recurrence recursive call, it will be from 2 to n. Okay, in the next call, it will be from 3 to n. So we have reduced the search space. Initially, the search space is n. Okay, so we will call this function linear search algorithm for, okay, let's try to call it. We will call it like this. Linear algo will pass the array A, okay, and in the current index, we will pass something like 0. Here the size of this array, and here some number like 45. We want to find out 45. This is the value of k equal to 45 here. We'll call it like this. So in the next iteration, for example, if we are saying that, okay, if A of this current index, so this is the call function, this is the call function. So if we didn't find it at 0th index, it will call the linear algo again, like this, 1, 0 plus 1, which is 1, n, 45, right? If these two fails, it will call this function again, linear search function again, by calling current index plus 1, right? This is the next call. And what is the next call? If we didn't find at the first index, okay, it will call this function again for second index, like it will be 1 plus 1, comma n, comma 45. Okay, it will go on. So now initially the search space size is n, which is input basically. Input is n. Then the search space size will be n minus 1. Then the search space size will be n minus 2. So we are reducing the input like this. And at each step, the effort is constant. We can write it as 1 also. So it will be tn minus 1 plus 1. Okay, and we have calculated the time complexity for it, which is order of n. Okay, so how can we reduce the time complexity from order to n to some lesser time complexity? How can we reduce the time complexity? So let's assume that this array is sorted. The array is sorted. Okay, let's assume. So we can apply binary search. Okay, so let me write binary search algorithm for you guys. Okay, so then we can discuss like what's happening in the binary search algorithm. So you have to note down this binary search algorithm. We'll come back to this page again. Okay, and we will see what's happening in the binary search algorithm. Binary search. We are saying that our array is A. Our search space is from ith index to jth index, and we are searching for k element, k value. Value is k, right? Here we are saying that our array is A, and our current search space for this recursive call of BS is I from I to J, and we are searching k. Okay. So we will say that if I is equal J, okay, and if A of I equal K, we found out the element. What does it mean? I equal J? It means that I'm adding comment here. It means that this is comment sign. Okay, it means that we are saying that search space contains only one element. Okay, search space contains only one element. Okay, so right now this is the base condition where we are saying that I equal J, right? If this is the case, we will return index as the I. Okay, so ith index the answer. Else, we will say that return -1. Okay, so this is the base condition. Base condition. Okay. Now let's move on to the next condition. So the space is less here. So let's move on to the next page. Here we say that else, if this is not the base condition where search space size, what is the base condition? Search space size contains only one element. I equal J. It means search space size contains only one element. So if that element is equal to k, then we'll return the I, else we'll return -1. So if it's not the base case, okay? Not the base case. What we will do? We will say that mid equal to floor of I, J, 2. Floor. So what is the floor? So if let me highlight it here. If we say that 1.2 floor, it will be 1. Okay, what is the ceiling? 1.2 will be 2. Okay, so this is the floor function. We are taking mid as the floor of I plus j divided by 2. Okay, whatever our search space, we have taken the middle element of that one. For example, if search space is from, example, if search space is from 4th index to 8th index, right? 4th index to 8th index. So what will be the mid? Mid will be 4 plus 8 divided by 2 floor function, which is 12 divided by 2, which is 6th element. So these are the indexes. Remember, I and j are index. So mid is also index, right? So we are going to consider, we are going to look at the middle element, which is the 6th element. Okay. So now let's see what is our next step now. We'll say that if middle element is equal k, then we found the element. Okay, let's return the middle element, mid. Else, okay, now look at these steps carefully. Else, as the array is sorted, using this middle element, we can reduce the search space by half. Right now, the search space is from I to j. Okay, so let me write it in green color here. Right now, the search space where we are looking the element is from I to j. Here, some middle element exists. Okay, and the array is sorted. These elements are assume that these are in ascending order. A, S, C, N, D, I, N, G. Ascending order, increasing order. Okay, increasing order. So right now we are at some middle element, and we are saying that okay, this middle element is not equal to the element that we are trying to find out. Then what we will do? We will say that if this middle element is greater than k, okay. If its middle element is greater than k, it means that k lies somewhere in between middle and j, right? So we'll call the binary search algorithm and we will reduce the size of it. Sorry, if the middle element is greater than k, it means that the k lies somewhere between I and mid, right? Because this middle element is greater than k and the array is sorted. I'll solve using one example also. Right now, I'm telling you in the generic language, right? That the k lies between I and mid. Why? Because this middle element is greater than k. Simple. So we'll write it like, now the search space will be between I, comma, mid minus 1. Okay. Very simple. Else k lies here. So now the search space will be, we'll call the recursive function, and the search space will be mid plus 1, comma j. Okay. So now we reduce our size from this to this only. Okay. This is our algorithm. This is our base case, which says that if it contains, our search space contain only one element, we'll compare that element and we will know that whether our element exists there in the array or not, if array is sorted, right? Now, if array is sorted, we'll calculate the middle element. And we will check that if that middle element, this is the index of middle element, mid is the index of middle element. Okay. and we are looking for the index only because we already know the number is k, right? So if a of mid equal the number that we are finding, we will return the index. If it's not equal, we will see in which space we have to find out the number. In which space we have to find out the number. Okay. Now let's assume an example that from 4th index to 8th index, we have some numbers like 10, 20, 4, 5, 6, 7, and 8. 10, 20, 30, 40, 50, right? Okay. And we know that we already calculate the mid. Mid is 6, right? Mid is 6. This is the array. This is the current search space for the array. Current search space for the array, where we are looking the element from 4th index to 8th index. We'll say that mid is 6. Okay, we have calculated mid, which is 6. We'll compare the 6th element. A of 6 is 30. And we are looking for k equal to 40, for example. We are looking for k equal to 40, which are not equal. Which are not equal, right? So our mid lies here. This is our mid. Now where we have to search the k? Either in this section we will search the k, or in this section we will search the k, because we have already compared the mid. As we know that this k is greater than our mid, we will search in this space. Greater means on the right side we will search of the mid. If mid is greater than k, then we will search on the left side of the mid. As simple as that. So right now, let me construct a tree for you guys. Let me consider an example where we say that array is 10, 20, 30, 40, 50, 60, 70, 80, 80. Okay, we have these many elements. So what is the index? 0, 1, 2, 3, 4, 5, 6, and 7. Okay, we have total 8 elements with 0 to 7 indexes. Okay, and we are searching for k equal to 50. K equal to 50. We are searching for k equal to 50. Okay. Now let's say that it is saying initially we will say that binary search pass a I equal to 0 initially and j equal to the last element 7, and we are searching for k equal to 50. This is the initial call we will make. This is the initial call we will make. Okay, initial call we will make. Now here the base condition won't be satisfied as search space contains 8 elements, not 1. Initial base condition is not satisfied. It will calculate the mid. It will calculate the mid. Mid equal to 0 plus 7 by 2. Floor of this, which is equal to 3. Okay, so if you see that it's 3.5 divided by 2, which is equal to 3. Okay, so now it will see that a of 3 is basically, a of 3 is what? This one, right? 40. This is less than k, which is 50, right? 30 is less than 50. So now the search space will reduce from the whole search space to exactly half of it, at half or half plus 1 only. See, we in single step, we reduced search space to half, exactly half. Okay, so we have ignored all these elements. Now we are going to search for the element 50 only in the right array, only in the right side of the mid element. This is mid. We will look for our element on the right. We'll never go back to the left side, right? In the next step, we'll call that BSA, the mid is 3, so it will be 4, 7, 50. See now. Initially, the search space is 0 to 7. Now it's 4 to 7 only. We reduced it to half in a single step, right? So now you must be getting this feeling that our recurrence relation will look like something like this, right? Where we are reducing the input from n to n by 2. If your understanding is right, then you may conclude that our recurrence relation will look something like this. Okay. Right. So let's execute this again. Let's write our array in the next page again. A equal to 10, 20, 30, 40, 50, 60, 70, 80. Okay, now this was the middle element initially, and we reduce our subspace to this one. Okay. Now I is equal to basically 0, 1, 2, 3, 4, and j is equal to 7. What is the mid element now? Again, we will calculate the mid element, right? As per the algorithm. If you go back and check the algorithm, we will again calculate the mid element. As the recursive call happens, this is the BS binary search. As recursive call happens, it will again calculate the mid element because base condition is not satisfied. Base condition where search space contains only one element. Okay. So now the mid element is equal to 4 plus 7 divided by 2. Okay. Which is what? So this is 4, 5, 6, and 7th index, which is what? 11 divided by 2, which is basically 5, because it's a floor function, right? So the value is 5. So now we will check with this element. This is mid. This is the mid element now. This is our mid, current mid. So now it will compare. It will say that, okay, let me compare the middle element. A of mid is basically greater than K, which is 50. It's greater. Okay. So as per algorithm, this step will execute. Okay. A of mid is not equal to our element. Now we will look for the reduced search space, which is BSA, and it will be called from I equal to 4, mid minus 1, which is again 4, and we pass 50 here. Now if you see, we are calling BSA 4, 50. Now this is I, this is j. Now the base condition is satisfied. I is equal j. The base condition is satisfied. I is equal j. Right? I is equal j. Now we'll compare the A of I or A of 4. If it's equal 50, which is equal 50, will return 4. So our answer is 4, fourth index. And the fourth index or element is slice. It's as simple as that. At each step, we reduce the search space exactly in half, and we will check the middle element. If middle element is equal to our element which we are looking, then it's okay. We'll return the middle element index. Else, we'll check whether our searching element is greater than middle element. If it's greater than the middle element, we will search from mid to j. Else, we will search from I to mid. Okay, I to mid minus 1. Now, if you see, we are reducing this part. This part is basically Tn by 2. Rest is 1. This is order of 1. This is order of 1. Right? So we can write the recurrence relation in the. So to build a recurrence relation from a recursive function, you have to look for the search space or input, number of input we are having. Right now, we are searching from I to j index. So I to j is our search space or input, and we are reducing the search space in half at each step. So we can write the recurrence relation as like this: Tn by 2 plus 1, something like this, or C. You can write C also, or write 1 also, because C is also order of 1. C is constant. And we know that the time complexity for this is log n, order of log n. So that's why binary search takes order of log n time. Cool. And we are good here. Right. And now let's see some example. For our next divide and conquer problem, binary search is done. It's done. It's divide and conquer. How is it divide and conquer? We are dividing the search space into half and half, and we are merging it again. So this is divide and conquer. The next step is merge sort. MERGE, merge sort. So here, what is sorting basically? We are given with an array, right? Array with some element, and we have to sort it so that it looks like in ascending order. Generally, we sort it in ascending order, right? For example, if our array is given like 25, this is our given array, and this is our sorted array. A dash is sorted array. So A dash, if given array is 25, 15, 68, 42, something like this. So our sorted array will look like 15, 25, 42, 68. Okay, so this is our sorted array. Here we will have a minimum element. Here we will have maximum element. And this element is basically greater than this one and less than this one. Similarly, this 42 is greater than 25 and less than 68. Okay, so this is sorting. How merge sorted is performed? So let's consider an example here. In form of graph, we will see it. In form of graph. First, we will look the algorithm in action. Then we will try to develop the algorithm out of it and various steps of the algorithm. Okay. So let's assume that our array is this. It's 25, 15, 68, 42, 91, 77, 35. This is 91, 77, 35, 197. Or 197, sorry. 197. Okay. This is our given array. I have chosen a random array. Okay. So now you can see that this is not sorted. So how can we sort it? Using merge sort. So the first tree node would look like something like this. This is the array for initial sorting. The sorting space would look like something like this. 0 to 8. This is 0. This is 0. 0th element, first, second, third, fourth, fifth, sixth, seventh. Okay, so it is basically 1 to 7. 1 to 7. 0 to 7. Okay. This is our first recursive call that we are making. We are passing the array and we are passing the start index, which we have to sort, and the last index, which we have to sort. Okay. So we are saying that in the first call, we are going to sort the whole array. Now we will divide the problem into two parts. Okay. Here we say that we will pass the whole array, and we are saying that, okay, now the sorting will happen only on 0 plus 7. We'll calculate the mid, divided by 2. So it will be 3. Okay. So we are saying that from 0 to 3, this recursive call will sort it from 0 to 3. 0 to 3 element. It means that 25, 15, 68, and 42. This part, this recursive call will handle, and we will make another recursive call, one more recursive call. In the binary search, we were making exactly one recursive call at each step, at max one recursive call, right? In the binary search. Here we are going to call two recursive calls. We are saying that, okay, this recursive call will sort from 0 to 3, and this recursive call from 4 to 7. Okay. Then we'll again make a recursive call, and this will sort from 0 to 1. Okay. And this will sort from 2 to 3. Similarly here, this will sort from 4 to, if you calculate mid, 4 plus 7 divided by 2, floor function, it will be 11 by 2, which is 5. Okay. So 4 and 5 will be taken care by this one, and 6 and 7 will be taken care by this one. Now, what happens that we have exactly two elements at each step. At each step, we have exactly two elements. What are those elements? 0th and first element. Okay, let's write the element at each step. Here we have 0 and 1 are 25, 15. And effort at leaf level is order of 1. Why? Leaf node level, leaf node is order of 1. Why? Because we have exactly two elements. We can either swap them. Okay, we can either swap them. If we have only one element, we can return the same element back. Now we have two elements. Okay, so we know that 0th index is the first index. Let's swap them, because 15 is less than 25, and it is on first index, which is greater than 0th index. So let's swap them. So they will be swapped, and we will return 15, 25 here back to this node. Here we have 2 and 3. 2 and 3, 68 and 42. So initially 68 and 42, right? 2 and 3 are 68 and 42. 68 and 42. Now 42 is less than 68, but it lies at a greater index, so we have to swap them. So let's swap them. So it will return what? 42, 68. To return these elements here. Now here, this node is responsible to sort the element from 0 to 3. 0 to 3. Now we don't have two elements or a single element. We have 4 elements, right? So we have to do some algorithm here so that we can combine two sorted array, right? Because this node is sorting its own array, this node is sorting its own array, and we have to combine these two sorted arrays so that 0 to 3 elements are sorted. Okay, before going back to this node, 0, 1 are sorted, 2, 3 are sorted. Now we have to combine 0, 1 is sorted array, sorted sub array, and we have to combine 2, 3 is sorted sub array. So what this step is doing? This step is basically combining two small sorted sub array. Okay, and this is called merge step. This is called merge step. And how this is done? Let me tell you how this is done. Okay, so we have two sorted array. This is you can consider A1. This can be considered as A2. Okay, A1 is 15, 25. A2 is 42, 68. And we are making a larger sorted array, which is basically a 0, 1, 2, 3, from 0 to 3 index. Okay. Here, initially, this is called merge algo. Not merge sort, this is merge algo. Merge algo. Okay. So merge algo is quite important. I will take a bigger example now, and I will tell you how can this be done. Instead of taking two small two-size array, I will take large, very large array. Okay, two very large array, two very large sorted array. Okay, so now we have two arrays. For example, A1 is 10, 20, 30, and 40. Sorry, 40. So merge algo is basically if we have two sorted array and we want to have a combination of these two sorted array in a single sorted array, merge algo is the optimal way. Merge algo is the optimal way. If we have two sorted arrays and we want a single sorted array, merge algo is applied. Okay, so now here we have 11, 21, 31, 41. Okay, so initially the index you can consider P and Q. This is 0, 1, 2, 3, 4, 0, 1, 2, 3. Okay, consider these as the two separate sorted arrays. So initially P is at 0 and Q is at 0. Whichever is smaller in P and Q will take place here. 10. Okay, 10 is smaller than 11. So we know that A of P was smaller than A1 of P was smaller than A2 of Q. So we'll increase the value of P. We'll increase the value of P. Whichever element has put here, corresponding to that index will be increased. So P will move here. Now we know that 20 is greater than 11, right? So we'll put 11 here and we'll increase the value Q here, right? So now 20 is less than 21. So we'll put 20 here and we will increase the value of P. Now 30 is greater than 21. So 21 has to go here and we will increase the value of Q, right? Now 30 is basically less than 31. So 30 will go here and we will increase the value of P. 40 is greater than 31. So we'll increase the value of Q. And we'll put 31 here. Sorry, 31 here. Right? So how comparisons are done? Let me write the comparison step. First we compare 10, 11. Then we compare 20 to 11. Then we compared 20, 21. Then we compared 30, 21. Then we compared 30, 31. See, we are comparing like this. We compared 30, 31. Then we compared 40, 31. Then we compared 40, 41. Okay. So now we compare 40 with 31. Now we will compare 40 with 41. 40. Okay. Now P is already exceeded. Once P have reached its limit, the another array will be placed here, whichever is remaining in another array, because if P have crossed the array indexes, it indicates that all element of A1 is already processed and the remaining element of A2 are greater than the last element of A1. Okay, so you can put 41 here. So it's not 40, 41. So this is the merge step. If you understand this algorithm, merge algorithm, we are having two sorted arrays. Initially, the variables are placed at the 0th index of both the arrays and we'll compare it. Whichever is lesser, we will increase that variable by 1. Okay, so now let's go back to our example. Here you know that 15 is greater than 42. 15 will be placed here and will increase the P value to here. 25, Q will remain same. 25 is less than 42, so 25 will be placed here. Now P A1 is already processed. It means that the last element of A1 in sorted array is less than the remaining element of A2. So we can simply put all the element of A2 here, 42, 68. Okay, so here the whole array is sorted as 15, 25, 42, and 68. Okay, and this will be returned here. Similarly, all the steps will be performed here, and this will be returned here. And here again, we will have two sorted arrays. One is this 15, 25, 42, and 68. One is this 35, 77, 91, and 197. Okay, 35, 77, 91, and 197. And we will use the merge algo to basically, so again we have a sorted array at the last root level, two sorted arrays, 15, 25, 42, 68. One is this one, and the one is 35, 77, 91, and sorry, and 197. Okay, so we will do the merge algorithm. This is P, this is Q. Okay, merge algo. 15 is basically less than 35, so 15 will be placed here. We will increase P. 25 is again less than 35. 25 will increase P. Now 35 is less than 42, so we will place 35 here and we will increase Q. 42 is less than 75, so P will be increased. 68 is less than 77, 68 will be placed here. Now P have exceeded the last index. It means that the remaining element, all the remaining elements are greater than the last value of this first sorted array, and vice versa is also true. Okay, so we put all the remaining element here, 77, 91, and 197. Okay, now if you see, if we pass this array using the dividation part, first we divide it using mid until we reach to at least at most two elements. Okay, at most two elements. We are having at most two elements here. And we do the merge step. Once we go back, we do the merging. At the root level, we also do the merging. And at last, we will have a whole merged array. Okay, now let me write the merge algorithm here. It's quite short, quite simple and short. So we'll do merge sort algo. This is merge sort algo. Okay, we'll say merge sort. MS means merge sort. Initial space is ij. Okay, we are applying merge sort on ij. We are saying that if I equal j, then return a of I. Okay, we are having only one element here. Else calculate the mid. Calculate the mid, which is basically I plus j divided by 2 floor of it. And apply merge sort on a comma I comma mid, because we have to include the mid. Merge sort on a comma mid plus 1 comma j. Here we are not looking for the mid part. We are not searching anything. So we have to include the mid either in this merge call or in this merge sort call. Okay. Once we have the merge sort, for example, we call the merge sort. Now we have a sorted array from I to mid. And this will give us a sorted array from mid plus 1 to j, right? But the whole array from I to j is not sorted. The whole array from I to J is not sorted. Okay, so we have to merge these two. So for this, we will do merge algo. Okay, merge algo. So if we get an array A1 here and A2 here using these two, we'll do merge algo on A1, A2. And we'll return this A3, we'll return this A3 here. Short and sweet, right? So what is the merge algo? I already explained what is the merge algorithm. I will write this algorithm again, and I will explain that how merge sort I, J. Let me clearly write this down so that I can explain the time complexity also. A, I, J. Okay. I'm saying that if I equal J, right, return A of I, else mid equal to I plus J divided by 2. Merge sort A, I. A small a is array here. Here I am writing array as a small a, not capital A. Okay, small a. I, mid. Merge sort. This same function I'm calling. This same function merge sort I'm calling here. A, mid plus 1, J. Okay. And I'm doing merge algo here. To merge, I got A1 from here, A2 from here, and I'm doing merge algo on A1, A2, merging two sorted arrays into single sorted array. Okay, merge algo. And I'm returning A3. Okay, something like this I'm doing. Now, what's happening? Actually, I should not assign this. Using this arrays like structure, because I'm using intermediate array at somewhere else. Okay, at the merge algo, I'm using intermediate array at merge algo only, right? So I should be assigning it some indexes, right? So I will apply merge algo like this. Merge algo A. I'm saying that these are the arrays from I to mid is one array. These two indexes indicates first sorted array. Mid plus 1, J indicates second sorted array. Okay, and I will return A. Final sorted array is A. Okay. So how much time do you think merge sort have taken? This is the worst case, right? And the number of comparison are basically order of n. If you see that n means total elements. These are the total elements. And this is outplace. What is outplaced? Where we have to use another space, like these are two sorted arrays, right? Right? And we are using a third array to combine these two. We are using a third array to combine these two. So we are taking extra space of size order of n. So that's why it's called outplaced. Okay. So in case of outplace, anyway, we have to fill all the spaces of array. That's why it's order of n, right? So as many, so for example, we have here some n1 elements. Here we have n2 elements, and then n order of n means n equal to n1 plus n2. Okay. And N is basically size of the final sorted array, final single sorted array. So that's why merge algo will take order of n. Merge algo will take, this will take order of n. Okay, merge algo will take order of n. Right? Now, in each iteration, we are taking n effort. We are not doing one effort. We are doing n efforts, right? And we are making exactly two recursive calls. So let's build a recurrence function, recurrence relation for this. Here, Tn will be equal to Tn by 2 plus Tn by 2 plus n. How 2Tn by 2? We are calling the same method 2 times, like this. This is exactly half, n by 2. So here the space is n by 2. This is exactly half, n by 2. Okay. And at each call, we are taking order of n. N means from I to j. This is the merge algo. Merge algo is outplaced. Remember, it's outplaced. So this can be denoted as 2Tn by 2 plus n. And let's solve this using master algorithm, which will be quite easier. I don't have to build a tree for that. Here a is equal to 2, b is equal to 2, and fn will be n. Okay. So what is n log base ba equal to n log 2, which is basically n. So this will be the third case, where fn is equal to n log ba. So the answer is fn log n, which is n log n. Okay, remember, always remember. Here, if somebody asks you what is the exactly space I am taking in merge sort, it is around 2n, because one array is sorted in the given array A for capital A. Another array is used for what I'm saying, another array is used for this sorting, outplace. It's greater than 2n actually, because I have to build a tree for this space complexity analysis. But right now the time complexity, if understood, it's order of n log n. And right now, thank you all for joining. You can go back and check some of the recurrence relation solving part, so that you will know that how this recurrence relation is built for merge sort. Okay, I try to explain as good, like I tried my best to explain this building of recurrence relation using this and solving the time complexity, so that you don't have to mug up the time complexity in merge sort. Similarly, I will go for a quick sort in the next lecture. Thank you all for joining, and bye.